Right, so what are reciprocal functions? So this one's pretty easy. So you know that if you had just x, the reciprocal would be 1 over x. That's pretty straightforward. So it's pretty clear to say that if you had a function f of x, then the reciprocal of that would be, so it would become 1 over f of x. And so as a result, the general formula for reciprocal functions is, well, not f of x, is, oh actually yes, we do want that. The reciprocal of this will become k over x, like that. So say you've got a graph and you're looking to find the reciprocal of the function fx that it provides. There's a few points you can look at, and this applies to, say, you've got an actual equation, you want to look at different parts to be able to find the reciprocal of it, to be able to graph it. There's a few points you need to look at, and let's just draw a simple graph so we can try and explain this the best we can. If we have a graph that is like that, and we've got our zeros here, as it describes in that, these will become vertical asymptotes for the reciprocal function, like that. Now let's just say, now to try and cram this in, we've got another function like this, which, I don't know, has maybe graphs that randomly look like that, with a vertical asymptote in the middle. That will end up becoming a graph with 0, something like that or something. So that represents that second point. And then local maximums and minimums. So as we, on the first graph here, that's a local minimum there. So that will become a local maximum on the reciprocal of that, and then vice versa. If that was a maximum and it went like that, then that would become a minimum for the reciprocal. And then we've got these two last points here to consider, is when f of x is more than 0, the reciprocal will be more than 0, and when it's less than 0, then the reciprocal will also be less than 0. And then also when, on the second one here, when f of x approaches 0, the inverse will approach positive or negative infinity, and when f of x approaches positive or negative infinity, the reciprocal will approach 0. Alright, so for the first question, we're just going to look at the general structure that reciprocal functions create in regards to their graph. So in this question, we've got both f of x equals 3 over x, and we've also got g, that's a crappy g of x is equal to negative 3 over x, so pretty similar. So I'll just create a graph, make it closer to the middle, I reckon. Decent size. And we'll try and do this one proper, so we'll draw some arrows onto it. And y and x axes. Alright, awesome. So what we can do is we'll just look at fx first. There's a few ways that we could create this graph. One is we could, if you have access, you can put the function into a graphics calculator. So you can put in 3 over x and negative 3 over x into a graphics calculator. But one of the ways you can get the general structure of the graph is to look at individual points by putting in the x, different inputs for x. So if we have, for f of x, let's just say we create a little table here, and we've got x and y. So what we'll do is we'll put in a few different values. It's ranging from negative and positive, so maybe I'll start with negative 4, -3, -2, -1, 0, and it's going to need to be longer, isn't it? 1, 2, 3, and 4. So then you can use a calculator for this, or if it's a pretty easy scenario, you can just do it in your head. So first we've got -3/4, then we've got -1, then we've got -3/2, and then we've got -3, and then this is undefined because you can't divide something by 0, and then we just got 3/2, 1, and 3/4. So just looking at specifically, I'll do it in green, fx, we can see that as we go from negative to positive with the x, we go on about this kind of route here, and then once we get past the 0 point, which is undefined, then I might mark that in red, and I'll just show that we have a vertical asymptote there with x equals 0, and then it goes round about down like this as well on this side. As we can see, when this goes down that way, values for this decrease in the y. So that's pretty good for that. And what we can do is we can just put a few key points that aren't too confusing. So I might notice that these ones and these ones are whole numbers, or that is as well, and that is as well. So I reckon what we'll do is just put some points along it, and we've got -3 and -1, and let's just say around about here we've got the opposite of that, so -1, -3, and then do the same for up here. We've got about 1 and 3, down here we've got 3 and 1. But then what we can do is we can do the same for g of x. And to make it very clear, we'll put that one in blue, and we'll create our x and y tables here. And then I reckon we can do similar values, so -4, -3, -2, -1, 0, 1, 2, 3, 4, like that. So -4 just have normal 3/4, that will just have normal 1, that will just have normal, so positive 3/2, that one we should just have positive 3. This is also undefined because we can't divide it by 0. This will be -3, this will be -3/2, this will be -1, and then -3/1. So you might notice that that's kind of like opposite for these two, which is interesting, but that should work well for the graph. So if we try and graph that, it should look around about like this, and then like that, because as the x becomes more positive on the left hand side, we increase, and then on the right hand side we decrease for negative wise. So then what we can do is also label some points, -3, 1, and -1, 3, and then here is 3 and -1, make that dot clearer, and 1 and -3. What you can see very clearly in this graph is that, particularly in this scenario, because we've got the general structure where we've actually got a numerator and a denominator, and the numerator is a real number, you can see that we're going to have that vertical asymptote at x equals 0, as you can't obviously divide something by 0. Then you can also see that that vertical asymptote divides two sections, one in which it's on very different quadrants, so it's not like it's like this, and that's because of the negative and positive values that actually completely change the vertical position of these graphs. Alright, so now we're going to graph some functions, and then we're going to graph the reciprocal of those functions. And so the first one we're looking at is we've got y equals root x, and y equals, so the reciprocal of that, 1 over root x, sorry. So what we're going to do is we'll create a graph, and this one will only need this here, so we'll do that. And you can definitely use graphics calculators to aid in this process, so that does help. But what we're going to do is we're first going to have a look at, we'll create a table for root x, and so we've got 0, 1, 2, 3, 4, all the way down to, that's probably all we need, won't it? And then what we can do is we can start filling this out. So we've got 0, we've got root 1, we've got root 2, root 3, and this one we can just write as 2. And so then it's pretty clear that as we go along the x path, we are increasing. However, the rate of this increase is slightly less. So I might circle that so we know which one it is, and we're just going to draw a graph that looks around about like that, and then label it y equals root x. Now obviously we could do a simple table to find out what the reciprocal is, but we can also have a look at this section we've got here. So we can see two main things that apply to this one. So we've got, and you might not have noticed this, but we've got this point here, and I might even label it for you at 0, 0, which is a, do this in red, 0 point here. And then we've also got in this section here, specifically as fx approaches infinity here. So what we can do there is, I can create a table also, but I think I might leave that for now, is we'll look at these points specifically. So we know that 0 point is going to become a vertical asymptote. So we can do that and label that x equals 0. And we also know that since I might write this down, since when x approaches infinity, so as x increases this way, it's pretty clear that root x also approaches infinity. Even if after each step that the amount of change decreases, it's still approaching that. So therefore, using that rule, it is clear that 1 over root x will actually approach 0. So if it's approaching 0, it means it's going downwards. It doesn't touch 0, but it approaches it. So then what we can infer from this graph is that obviously we've got that vertical asymptote there. So it's going to start somewhere, because it's approaching 0, it's going to come down and look a little bit like that. And then we can quickly label that graph y equals 1 over root x. Alright, so the next question, we've got a little bit more of an interesting one. We've got y equals x plus 1 and x minus 3. And we also have y equals 1 over x plus 1 x minus 3. And so this graph is going to need a decent amount of space. And we've got that like that. And right off the bat, because we've got these 2 points here, we know that we're going to have zeros at those points. So we know that we're going to have zeros at x equals -1 and x equals 3 using these 2 parts. So we can then label that on the thing using this colour here. And we can say this one's, might need a bit more room for that actually. About there. That one's for there, and then we got 3, and let's say that's about there, so it's going to pass through those points. And then what we can do is we can just create a little table quickly again and just have a look at a few values. Obviously for x and y. Have a look at -2, -1, 0, 1, 2, 3, and maybe 4. So -2 is going to give us 5. -1 will give us 0. This 0 will give us -3. 1 will give us -4. 2 will give us -3. 3 will also give us 0. And 4 will give us 5, like that. So it's clear that the minimum for y occurs there, so we'll create a point for that. It should, which we know that because we know that a local minimum will occur between the 2 zeros, and if I was to have a look at both of them, we know that the difference between these two is 4, so it's going to be 2 less than that, which is that 1 that we got there. So just have a look at that, which we can label as 1 and -4. And we know on either side it increases, and we can even see that from the points. So we can estimate that it's going to look a little bit like that. And that one will be similar, looking a bit like that. And I might just label these ones. Oh, that's crappy labeling. As 3 and -1. Alright, so now we've got to find the reciprocals one. So we know that we have 2 different zeros, so they're going to become vertical asymptotes. We don't have any vertical asymptotes on here. We have a local minima, both of which will help us graph this. So to start off with, I reckon we draw the asymptotes. So these are one of my favorites and easiest parts. We can just draw some vertical asymptotes, just make sure we label these along there. Alright, and then the local minimum will become a local maximum. So the question is, so we know it's going to be along this line, the x = 1 line. So what we can do is we can just input that into the function. If we have a look at that, if we put x = 1 into that, we'll get 2 times by -2. That should give us -4. So we'd have, I can just write this here, when x = 1, that equals -1/4. So then we know it's going to be, make sure we do it in blue, about here somewhere, round about. I might as well label that as 1 and -1/4, like that. Now I might just create a little table to help me graph all this, and I'll just do a quick one so I can get an idea of some of the points. So if it's before the asymptote, so -2, -1.5, and then we already know what it looks like in the middle because we got local maximum, and then on the other side I can put a 4 and a 5. Sure, that works, and I'll just put that into my calculator. We get 1/5 here, and for this one we get 4/9, and this one we also get 1/5, and then this one we get 1/12. So it's pretty clear from these values, and I'll draw the middle part first because that's easiest, because we've got these vertical asymptotes, so we know the middle part's within those, and we know that we've got a local maximum, so these will actually reach up to touch the local maximum and reach back down so otherwise it wouldn't be a local maximum. And then for these other points, we can see here that it actually increases as x increases. So it's going to look a little bit like this. And we know it won't touch the y equals 0 line, because if y was to equal 0 in that function, there is no possible scenario that can occur. It would just be undefined, because 1 over 0 is undefined, so it can't equal 0. So there we've got a horizontal asymptote there, but I shouldn't need to label that here. And then we can draw the other one. We see that for this one it decreases, so we can just draw this curve going down like that. And then what would be good for us to do, it's probably a little tricky, but we'll fit it in, is we'll just label this graph. So x plus 1 and x minus 3, yeah, it goes a little down here. And then this one, y equals 1 over x plus 1 x minus 3, like that. Alright, so here we've been given two graphs, and these are the normal function graphs. And so what we've got to do is we've got to find the reciprocal for both of them. So the first one, you should be able to recognize that this is very similar to the one we just did. And so we'll have at the zeros vertical asymptotes, and I won't bother labeling them for now. And we're going to have a local maximum where x equals 3 over 2. And we're going to take this one very simple, and because for the y we've got -2, like right there, we know that the reciprocal is 1 over -2. So we know we're going to have a point here at 3 over 2 and -1 over 2, like that. And so we're going to have local maximum here, and then we've got a very similar situation up here, because we know these follow the same paths as the other ones, so we can just draw them simply like that. Now for the next one, let's just focus on a few things. So we've got a 0 here, and we all know what happens with zeros. So I'll just do vertical asymptote along there, and I will label this one. And we don't have any more zeros, but what we do have, which is a little bit different, is we do have a vertical asymptote at x equals 4. And don't mind the horizontal asymptote here, because that applies to both the normal and the reciprocal of the function. So what we can do here is, looking at this, so vertical asymptote becomes a 0. So we know that this function will actually pass through the x-axis at x equals 4. And so to be able to find the ways, so we've got these points now, but to be able to find the directions in which the graph goes, we can look at a few other points. So specifically from here and here. And we can see that this line approaches -infinity. And so when that happens, this will approach 0, and that is specifically in the y direction. So what we might do is we might write some of this down, and I'll make sure we've got a divider between here. So particularly using this second line, so we're looking for between this segment, because what we have there is that fx is more than 0, so we're saying y is more than 0, so therefore 1 over fx, which is a reciprocal, will also be more than 0. So then what we can say is, or we can graph it actually, is that it will go that way. Then what if we look between this point? So we know that f of x is less than 0 at that point, so obviously 1 over f of x will also be less than 0. And so before we start to draw that, we'll have a look at this segment here. And so what we have there is we've got the top part again, and we know that it passes through this 0 point here. So what we can say is that it will look a little bit like that, but obviously we've got the horizontal asymptote there, and then that. So that's our function, and I'll label that 1 over f of x.